So good morning to all of you. So we have finished a simple regression and a basic R square analysis and residual analysis in yesterday's session. Today we will just discuss the meaning of standard error, and then we will discuss the problem which has been solved from your side, considering all individual independent variables x1, x2, and x3. Which independent variable is a good predictor of y, that you can tell me. You can explain your analysis to me one by one, and then we'll consider the case of multiple regression considering all independent variables together. We'll try to predict y, and we'll see what is the strength of our model and what is the standard error of our model. And based on this concept of multiple regression, then I'm going to share a few of complex data sets with you on WhatsApp group, like blood pressure calculation and IQ calculation and everything, for which I'll give some time, like 5 to 10 minutes to you, and you have to do the analysis of those data sets, and you have to present your analysis to me in today's session. So in today's session, maximum talk will be from your side. I want to see how you analyze data, what you interpret about that analysis, and what are your key findings from the data. So that is all about for today. And if time permits, at the end of the session, we'll also cover sampling methods. It's pending from day one. So we'll try to cover sampling methods also. It's a theoretical part. It will not take more than 15 minutes. So that is all about what we are going to do today. So first, I'll try to explain you what is the meaning of standard error. If you look at the regression output, we see multiple numbers like R square, adjusted R square, and then standard error. So what I'll do is I'll shift to the presentation for a moment, and just a minute. Okay, we'll just see what is the meaning of standard error, and we'll come back to the Excel. So this is the output what we have discussed in yesterday's session. Like R square was 0.17, adjusted R square was 0.14, error standard error is 371, and this is the ANOVA output which we are going to discuss from Monday. And this is the coefficient table. Coefficient of the value of b is minus 240, and the coefficient of x is 57.93. Now we have discussed that as per this available data. Now whenever I analyze data, I always use words very specifically. I always say based on available data. What I say, based on available data and the R square value, which is 0.17 only, I can say that my education is not a good predictor of earning. Now this claim is based on the available data. Maybe my data is insufficient, maybe my data is not complete, maybe my data is wrong, I don't know. Based on available data, I can say that education only as one variable is not a good predictor of earnings. Okay, and that is because of this R square value. Now I told you that R square tells the confidence in your model. From R square, you can visualize, or you can consider the confidence in your model. Whatever model you have, y equal to mx plus b in this case, because only one independent and one dependent variable we have. So for this linear correlation, linear regression, what confidence you have in your model is given by R square value. Now first we'll discuss standard error, and then I'll tell you what is the meaning of adjusted R square. Okay, so R square gives the confidence in your model. So only 17% of variance in Y is actually explained by X. So X is not a good predictor. So this is what we have discussed yesterday. So what is standard error? Standard error value is 371. Standard error value is 371. Standard error represents the average distance. Very important. Standard error represents the average distance that the observed values fall from the regression line. So actually, standard error talks about the accuracy of the model. Standard error talks about the accuracy of the model. So when I say that R square is only 0.17, what confidence I have in my model is only 17%. What kind of accuracy my model has is very less, because the standard error is huge. 371 is a huge value. So standard error represents the average distance that the observed values fall from the regression line. It tells you how long the regression model is on average using the units of the response variable. Now in our case, the response variable is earnings. That is the dependent variable. Response variable is also referred as dependent variable. Okay. So in our case, the response variable or dependent variable is earnings. And we have expressed earnings. If you look at the data, if you can switch to data on your machine, uh, the unit of earnings is the same for unit of standard error. So whatever units you are considering, I just explained yesterday that we can consider 77 as 77,000 or something 3,18,000, something like that. So if it is in thousands, so this even standard error is in thousands. So this is 371,000 is the standard error, something like that. So standard error tells you the accuracy of the data model. R square tells the confidence in the data model. Combination of these two will tell you exactly whether your model is a good data model or not, whether you can go ahead with that data model or not, whether you can implement the same data model on different other data sets or not, because this data set is a limited data set. We can say it's a sample. If I'm satisfied with my sample data, and if I'm okay with my sample R square value and standard error value, then I can implement the same model, same equation to predict earnings in different education values in different data sets. And now we are talking about inference, because based on sample study, we want to, or we are trying to claim something about my population. So in that case, if my data model is strong enough, if my data model is accurate enough, if my data model, I have enough confidence in my data model, then I can replicate the same data model in other data sets from the same population. So we are trying to create an inference from my sample study about the population. And for that, this R square and error value, standard error value are very important. And generally you will see these are directly proportional. If you have very less R square value, even the standard error will be on higher side. Okay, so that is another indication that whether you want to go ahead with that R square value or not. Suppose in this case, if you get the output instead of 371, in this case, suppose you get the output instead of 371 only 71, 3 is not there, suppose. That means the R square value, your confidence, your data model strength is only 17%. But even the standard error is also less, 71. It is very less. 71 is a small value. So considering standard error, maybe in this domain, even 0.17 to 0.20 is an accepted R value. That is what you can conclude using the standard error value. So standard error value is very important to do the analysis of R square. Yesterday we have discussed what value of R square we should accept or reject, how to decide. So it is one of the parameters. Of course, the first and most important parameter is the past data. In similar kind of situations, for similar kind of data in your similar domain, what kind of different R values have been accepted by different researchers and different analysis teams. Based on that, you can have a judgment about what R square value I should have to say my data is my model is a good model. But apart from that, even you can look at the standard error. If the standard error is less, even if R square is less, you can accept that model. So a lot of things are dependent on standard error. Right. So that is all about R square and standard error. Now I'll tell you what is the meaning of adjusted R square and how to use adjusted R square. Now, because we have solved problems with only one dependent and one independent variable, that is simple regression, there is not much use of adjusted R square in case of simple regression. Adjusted R square comes in the picture when we talk about multiple regression. That means when we have multiple independent variables, multiple X variables, and we have only one dependent variable, only one Y variable. Only in that case, the adjusted R square value is very useful. Now, what is this adjusted R square? When I say that adjusted R square is useful only in case of multiple regression, that means my equation will be of this form, something like this. It will be something like y equal to m1 x1 plus maybe m2 x2 plus m3 x3 and maybe then plus b, the constant. If I am considering three independent variables and if I am trying to use three independent variables to predict my dependent variable y, Now this becomes the case of multiple regression. This becomes the case of multiple regression. Now in case of multiple regression, if I'm considering multiple independent variables, I have to look for the difference between R square and adjusted R square. I have to look for the difference between R square and adjusted R square. If the difference is very small, in this case it is 0.03, which is very small. 0.03 is a very small difference. In that case, I can say that whatever independent variables I am considering on the right hand side of the equation are sufficient enough to predict my y. Now, because this is a single variable, I'll not go into this difference. I'll not say that our independent variable, which is education, is a good predictor of y. No, I cannot say that. Adjusted R square comes in the picture only in case of multiple regression. Now, in this case, I am using 3 independent variables, x1, x2, and x3. And in this, with 3 variables, if I'm going to get this kind of values for R square and adjusted R square, 0.17 and 0.14, with a difference of only 0.03, that means whatever x1, x2, x3, the 3 independent variables I have considered are good enough to be considered in the data model. Now, if the difference is huge, suppose this is R square is instead of 0.17, suppose the R square is 0.47. And then the adjusted R square is suppose 0.24, something like that. So in that case, the difference is huge of 0.2 something. So if the difference is huge, in that case, I have to reconsider all the independent variables in my equation. So either I have to exclude some of the variables. So maybe I have to exclude either x1 or x2 or x3 or maybe 2 variables, I don't know. Or I have to add another x4 variable, which is actually having some impact on y, which I'm not considering in my data model. So this difference, if difference is huge between R square and adjusted R square, tells me whether the independent variables which I'm considering in my data model are sufficient enough to predict my y or not. So you can see the explanation: R square and adjusted R square are close enough, means not much chance of adding or removing any predictors, any independent variables. So that is the meaning of adjusted R square. So when you combine the analysis with R square, adjusted R square, and standard error, you can tell a lot of things about your data model. First thing, what is the confidence level in your data model? Second thing, what is the accuracy of your data model? And third thing, do you have sufficient and enough number of predictors or independent variables in your data model? If the answer to these 3 things is positive, that means your data model is very good. And you can go ahead with this data model to predict some other data sets from the same population. And you can do this regression analysis, or you can use this regression analysis for inferential statistics. So that is what all you can decide based on only these 3 values: R square, adjusted R square, and standard error. Am I okay? Is it clear to you?
Yes, sir.
Okay, very good. Now, looking at the coefficient table, you can see the intercept is at -240, which is the constant, and the education value is 57.9338. So these are the coefficients in the your equation. So in case of multiple regression, you'll have multiple independent variables in this table also. We'll see that once we'll start with Excel. It will give the individual standard error also. So you can see the major standard error is in case of intercept, which is a constant. This also indicates what is the meaning of the standard error for intercept is on higher side, even higher than very close to the standard of complete data model. This indicates that the default value of earnings for the basic level of education, that itself is on higher side. So if I am by default considering that if I am 12th pass, I should be earning this much of money. If I'm graduate, I should be earning this much of money. And if I'm postgraduate, I should be earning this much of money. That basic assumption that what amount of earning I should have for my basic qualification, that basic assumption itself is on higher side. That means the intercept standard error is on higher side. Because of the basic assumption, there is a gap in the basic assumption itself. All further x values are predicting wrong y values or predicting higher y values. So that is another analysis from the individual standard error what you have from this coefficient table. Now in this coefficient table, you can see other columns like t statistics, p value, and this is the lower and upper levels of 95% of confidence level. Now you do any kind of analysis using any kind of tool in this world, the default confidence level is always considered as 95%. And that is also linked with your standard error. How? Now standard error tells, for this example, my standard error value is 371. So what is the meaning of this standard error and 371, and what is the connection? I'll just try to explain that, just a minute. Okay. So the standard error and the confidence level of 95% are also linked. How? Now this is a thumb rule. You should remember this thumb rule. Approximately, if I'm going for confidence level of 95%, approximately 95% of the observations, approximately 95% of the observations should fall within plus or minus 2 standard error of the regression. Approximately 95% of the observations should fall within plus or minus 2 standard error of the regression. So in this case, in our case, what is the standard error value? 371. So what is the 2 standard error value? Double of this. So double of this is almost 640, 650 value. So from your mean, 650 on both the sides. From your mean, 650 on both the sides, plus or minus 650 from your mean, 2 standard deviation, 2 standard error from your mean. So 650 on both the sides is actually your set of accepted values. And beyond 650, all are your actually standard error related values, for which you can consider either them as outliers or you can try to exclude them for your analysis. Now this is also called as data sanitization. If you want to create a good data set out of the available data set, considering standard error, I can try to exclude those data points which are creating maximum error in my calculation of data model. So that is a bit complex analysis of standard error combined with the confidence level of 95%. So I'll not go into that much details of that, but standard error, using standard error and the confidence level, you can also try to predict the outliers in your data set, or you can also try to predict those data points which are trying to create maximum error in your calculation of your data model. So you can try to exclude those data points and recreate a new data set for fresh analysis. So that is also possible based on standard error. Fine. So now today we are going to discuss multiple.
I have a question.
Yes.
So during the wrangling process or cleansing process,
Yes.
can this process be implemented iteratively, or because every time we iterate through, we are going to lose some data, but at the same time we are going to build more concentration of the data points.
Correct.
So typically it's done iteratively, or it's only 1 or 2 iterations. Like how many iterations should be done for sanitization?
No, now there is no fixed rule or global rule for that. It depends on your own like company policies or your own assumptions, like what kind of data set you want. If you are okay with even 5% of outliers in your data set, and if you're going to get that after first iteration itself, you can stop at first iteration. But if you want all your data sets inside your third standard deviation, that means no outliers should be there. And for that, if you want to go ahead with 2 or 3 iterations, you can go ahead with 2 or 3 iterations also. So it all depends on what kind of data set is accepted in your case by your organization or for your analysis team. It all depends on some rules which have been defined previous to starting of this complete analysis process, that what kind of data is okay with us, what kind of R-square value is okay with us, what kind of standard error is okay with us, and then what kind of confidence level you want to have in your data models. If all these things are defined, then only you can decide how many iterations you can do for this.
Okay.
So based on our analysis, we see that none of the individual variables seems to be good predictors of infant mortality, which is our y-dependent variable. So we'll try to do the multiple regression, and we'll try to include all our variables in our data model, and we'll see what kind of data model we are getting. So if you want to do multiple regression, the option is same, the regression option only. So go to data analysis. In data analysis, you have to select regression, click on OK, input y variable, So this is your y variable. Input x range. Now instead of putting individual variable, now we are going to put all the x values including the labels. So I'm going to select all three x1, x2 and x3 at a time. Labels, yes, we have labels in my first row. Confidence level, keep it 95%, which is by default. Output, yes, I want to start my output suppose from this location, and I don't want residuals right now. I'll just go with plain data model first. So I'll click on OK, and this is what I get as my output. So R square value is very good, 0.84. Adjusted R square is 0.78, very close to R square. It's a difference of only 0.06 almost, which is very good. A standard is very less, 11.93 is a very less value for 12 observations. And then we have the coefficients also. Looking at the coefficients, I can write down the equation of the regression line. And it seems that this model is a good predictor of y. So individually this x1, x2 and x3, they may not be the good predictor of y, but in combination, when I combine these three independent variables in combination, they are trying to predict a very good value of y accurately, or very with very high confidence. So when I say R square is 84.59, I have almost 85% of confidence in my data model. And accuracy is also almost very good. 11 is very or rather 12, almost 12 is a standard error value. So combination of R square and standard error tells me that my data model is very good. I'm very confident about my data model, and the accuracy of predictions will be very good. And then the adjusted R square tells me that there is not much chance left to either exclude or include any additional variable. Still the difference is there, but the difference is not significant. And then from the coefficient table, I can get the numbers using which I can write down the regression line equation, using which I can then predict a few values of y which are not with me. Or I can try to implement the same model on different data sets from the same population or the same countries maybe. So this all I can do as analysis from multiple regression, and this is the case of multiple regression. So what is the equation of this data set? If you can tell me the equation will be infant model equal to, the first variable is this and the coefficient is minus 0.677. So minus 0.677 into literacy rate minus 0.5982 into schooling level minus 0.0029 into GNP plus 154, which is the intercept. And if you look at the standard errors, the highest standard error is for the intercept itself, and that is also close to the standard error of the complete data model. So that is good enough to tell me that there is an initial assumption which I am considering for my data model for no value of x. That initial assumption itself is on some higher side, because of which I am getting even this error. Otherwise, even this error will not come. So maybe I have to include more data points in my data model, or I have to include maybe more variables in that case if I want to go ahead with more accuracy in future. That is an indication that my basic assumption, what I am considering for my intercept value, gives me maximum standard error, and which is close to the standard of the complete data model. So that is all analysis I can do. Now you can go for residual analysis also, and you can look at the different deviations also, and you can do the complete analysis of this data set. So overall, this data set is a good data model and with higher accuracy and higher confidence level. Now I can give you any values of x1, x2, x3, and you can easily predict y, and I can confidently say at least 85% confidence. I can have 85% confidence in my prediction that my prediction is accurate or close to the expected value. Fine. So I'll share that Excel sheet again. Same problem we have solved for multiple regression, yes, and this was the output. And based on this output, we have done the analysis of R square and everything else. Now look at the residuals. These are my residual values for all my observations. So I'll just copy the observation headings, like which are observations and what they are getting represented. So it will be easy for us to do the analysis. Okay, fine. So from the residual output, Look at the standard error. What is standard error? 11.9, almost 12. Now 12 is my standard error. So up to 12, when I say standard error is 12, deviation up to 12 is very well accepted. Deviation up to 12 is very well accepted. Deviation from 12 to 24, that is to standard error, what we have said for 95% confidence. For 95% confidence, deviation from 12 to 24 we are going to analyze, correct? But we don't have 95% of confidence. The R-square value tells us to go till only 85% of confidence. So considering 85% of confidence, that is 10% confidence less, maybe 12 to 24, I'll reduce it to 12 to 18 or 12 to 19. So up to 18 or 19 are my accepted values, seems to be, in terms of differences. Difference of 18 to 19 till 18 is okay. So now if I look at differences, this is the point which is going beyond what analysis I have done based on standard error and R square, because its residual is 20, which is way ahead considering 85% of confidence. And maybe there is a slight chance, no other variable. Okay, so others are 11, 16. Yes, maybe there is a slight chance because of the values that even I should consider this difference, which is 16.19. So apart from these two deviations, other deviations are very well within accepted range. And even I may go to 95% confidence also if I just exclude these two deviations. That also indicates me that out of all these countries, whatever variables I'm considering as predictors, these variables as predictors don't fit for Vietnam and Zimbabwe. So maybe for Vietnam and Zimbabwe, I should have a different data model. And for other countries, I can go ahead with the current data model. So current data model is not suitable only for specific countries. So I'll not say the whole data model is wrong, or I'll not say the whole data model has to be redesigned. No, current data model is good for these all countries, but I have to reconsider the data model for Vietnam and Zimbabwe. So maybe I have to consider a few variables which are local, specific to these two countries, and maybe I have to create separate data models, one for Vietnam and one for Zimbabwe. So you can also try to tell me how many outliers do you have for these data models based on your residual analysis. So if you consider a standard error as suppose 8.6 in this data model, that means any deviation which is beyond 15, 14 or 15 is kind of can be considered as outlier for this data model. So accordingly, you can just try to tell me how many data points you have or you can consider as outliers based on residual analysis for different data models. Now I'll tell you why residual analysis is very important. It is possible that it may happen that the age value is very good, like around 30, 32 is the age value. Fraction of life is also very less. So number of years spent in urban area is very less. Even the weight and height combination calculation is very good, and a pulse rate is very good, but still the systolic blood pressure is on higher side. That is a possibility that you are getting a higher blood pressure for a normal case also. So there can be some outliers, and there is a possibility also that you have a very large age value, 50, 55 plus, fraction of life is on higher side, weight and height calculation is not matching, pulse rate is very slow, but still the blood pressure is in control. So these kind of outliers may be present in your data, because of which maybe you are getting more difference in R square and adjusted R square, and you are getting more standard error. That is possible. So residual analysis becomes very important, that if I come to know that out of the whole data set, almost I have 40 data values, out of 40 data values, just because of one or two observations, if I'm getting all these numbers and this kind of deviation, it is better to exclude those couple of observations rather than to reject the data model itself. So if one or two observations, by excluding one or two observations, I can minimize this difference and I can minimize the standard error. It is better option to exclude those couple of variables. So always look at how many outliers are there in my data based on residual analysis. If those many data observations I can exclude and go ahead, then you can take a call on having same data model with exclusion of those observations. So Nandan, you can try to tell me how many outliers you have considering this standard error, how many outliers you have based on residual analysis for these three models. Yes.
Um, 8.6. Okay. So from the outliers perspective, I don't have anything about double the error. So everything fits in a 2 sigmas.
Okay. Any
The largest,
deviation in the range of 14 to 15 on both sides, plus minus?
no. The largest deviation I have got is positive 13, positive 12, negative 12, negative 11, positive 11.
Okay. So you got three observations of 13, 12, and 12, correct?
Yeah, 13, 12, and 11 on positive, and
No.
minus 11 and minus 12 on negative.
So all those observations which are 12 and beyond 12 on both the sides are two only, correct?
Yes.
So can you do one thing? Just exclude those two observations which are having 12 or beyond 12 and rerun this same regression on same variables and look at the R square and adjusted R square.
Okay. Doing it now.
Yeah.
Sir, just one doubt. The value whichever is above the standard error, that should be considered as outlier, right?
No.
Anything like what?
See, that's why I told you that it depends on what confidence level you have. So the standard thumb rule, as per analysis, says that at 95% confidence level, which is the default for all the calculation, at 95% confidence level, 2 into standard error becomes your accept range.
Okay.
2 into standard error becomes your accept range. So if the standard error is 8.6, approximately 15 to 16 on both the sides becomes your accept range.
Okay. Okay.
Okay. But we don't have 95% of confidence because R square itself says it is 66%. So considering 66%, I cannot go 2 into. So that's why I'm considering even 12 and 13 as outliers. I'm restricting myself to 10 or 11 on both the sides, as 66% of the confidence is there. Getting it?
Okay. Sure. Got it.
Yeah.
So with those numbers removed, I was able to get R square of 0.64.
Okay. Adjusted.
And then adjusted R square is 5.2.
0.52.
And standard error reduced down to 7.5.
7.5. Okay. So it is not solving our purpose, seems to be, because the difference is increasing from minus 0.1 to minus 0.12.
Both confidence and accuracy dropped, but error reduced.
Yeah. So if you want to compare only these two data models, So this what I have written is residuals. I find two outliers with plus or minus of 12 from standard error, considering standard error of 8.6. Adjusted R square has a difference of minus 0.1 from R square, based on which we took a decision that we should exclude these two observations and rerun the data model. After doing that, my R square is not changing that much. It's a difference of 0.02 only, that is negligible. So I'll consider the same R square, but adjusted R square is going down by 0.02 points. Even that is okay, but the total difference between these two is 0.012, 0.12. If I want to compare these two models, I don't see that much of difference in these two data models. Having difference of 0.1 and 0.12 is not a huge difference. First thing. Now, second thing is regarding the standard error. Yes, standard error is getting reduced by almost 10% or 11%. So there is a reduction of 11% in my standard error, which is very high, on higher side. Now, considering this as standard error, do you find any outliers based on residual analysis in the new data set? Are there any outliers which are beyond 12 or 13 difference?
There is one outlier which is 15. Nothing about 12 though.
Okay, so considering plus or minus of maybe 15, I'll say, which is on very higher side. So compared, if I want to compare these two models, my suggestion, my interpretation based on whatever analysis I have done for past 10 years, my interpretation is I'll go ahead with this model excluding those two observations, because I don't see that much of impact on the difference in the R square and adjusted R square just by excluding those two observations. Even if my difference is increasing by 0.02, I'm okay to accept that difference, because that is not suggesting a huge change in my independent variables that I should add or remove a complete variable. No. And standard error is getting reduced by 11%. That is a huge thing for me, because I'm going towards more accuracy, which is more important for me in case of blood pressure. And even I'm going to a reduction in terms of outliers with the residual analysis also, and that too on the higher side of 15. So I may consider this as a better model compared to the first model.
Okay, I did the resanitization.
Okay.
Another round of it after removing the outlier.
That one outlier.
So with the same x1 to x9 with that 15 outlier removed,
Okay.
and now I have a R square of 0.7026.
Very good.
And then I have an adjusted R square of 0.56, which is still 0.11. So it did not lose that accuracy.
So what is R square? 0.
R square is 0.70.
70. Adjusted R
And
square is?
adjusted R square is 0.59.
Very good. Excellent.
And error is 7.03.
7.02. 03. Excellent.
03.
Excellent. Excellent.
So yeah.
Almost 10%. And any outliers are there still?
So let me look at the outlier with the 7. So now I don't see anything even near 14.
Excellent. So this is a best model you can consider. Compared with the previous two, this is a better model. Yes, not available, not applicable. So this seems to be the best model, for which we have to exclude three observations out of 40 observations. Now, the main question again is, can I go ahead and exclude 3 observations out of 4 observations to get a better model? Again, yes or no. That depends on your own research. 3 out of 40 becomes almost 7%. That means I'm trying to exclude 7 to 8% of my data to get my model to predict accurate and a good confidence value values. So can I exclude 7 to 8% of data? Now again, I'll go ahead and tell you that it depends again on domain. Again, the domain specific numbers comes in the picture. In few domains, it is allowed even to exclude 25% of data. If you go to political science, the example which we have discussed yesterday for exit polls and something, even if you are excluding 25% of your data for your analysis to have a better predictions, that is allowed. In medical analysis, generally we should not exclude more than 5% of data. That is what is said generally. But still, 5% and 7% only for 2%. If I'm going to get a better prediction, yes, I'll go ahead with this model. So it seems like this model is a better model with very good R square value, very less difference in R square and adjusted R square. Even the error is minimized, and there are no outliers. Basically, all my data points are behaving as per my data model. So all the behavior is captured in my data model. So if I try to implement the same data model on different data sets from the same population, the probability is more that I'll predict more accurate values about the blood pressure. That is the complete analysis or comparative analysis based on whatever 1, 2, 3, 4, and 5. And to get this model even, you can see we have done 2 iterations of residual analysis, and that's how residual analysis is very important. The iterations can be done only based on residual analysis. For current numbers, you can do analysis using R square, adjusted R square, and standard error. But if you want to go into next level of analysis, next round of analysis, you have to do the comparison using residual analysis only. So after 2 iterations, we have got this model which is trying to predict the accurate values of blood pressure only for systolic. Similar kind of activity can be done for diastolic. And now you can see we have almost taken 30 minutes to arrive to this conclusion only for 40 data points and only 9 variables. In reality, you may have 40,000 data points and you may have at least 15 to 20 variables. And then you have to create a better data model out of that with a lot of iterations. And that's why analysis generally takes a couple of days or a couple of weeks to arrive at a better data model or a good data model out of the available data.